Thank you very much, and thank you to the organizer for this great conference so far. Okay, so what I will be talking about today is essentially the content of a recent paper that I published in collaboration with Keegan Flood and Eric Winter. And it's about non-commutative generalization of the notion of jet bundle and jet functors. Okay, so I will start with a brief introduction of what non-commutative geometry is essentially. So the starting point is the usual correspondence and duality between geometry and algebra. So we want to study a geometric object, and geometry is not as easy as algebra in a sense. So we would like to understand the geometry of an object through the algebra of some sort of regular functions over this geometric object. For example, we have in differential geometry, we have the algebra of smooth manifold. In complex geometry, we can use the algebra of holomorphic function. In the algebraic geometry, we have a variety, and we study the ring of algebraic functions over it. Okay, so usually the main idea is that we start from studying the algebra corresponding to a regular object, and what happens is that sometimes one generalizes the algebraic object and interprets it as the dual of a generalized notion of a geometric object. And that's precisely what happens in non-commutative geometry, because the idea is that we take, instead of taking an R algebra that corresponds to a geometric object, we take it non-commutative, and that already doesn't happen in standard geometry. Never happens that the algebra of regular functions over a geometric object is non-commutative. So let's see what happens with the object that we're used to study and what they will become, will be generalized to. Okay, so in geometry we usually start with a field of scalars. So it could be R or C, for instance. In algebra this is just a ring, and the generalization will be for us a commutative unitary ring. So this will be the scalars. Then geometrically, the geometric object is usually a variety, a manifold, and the algebraic object corresponding to it is for example, in differential geometry, the R algebra of C infinity M functions. And for us, this will be generalized to an algebra which is unitally associative and not necessarily commutative. When I say not necessarily commutative, I mean that the sum is still commutative, but the non necessarily commutative part is the multiplication. Okay, so then in geometry we have the notion of vector bundle, and algebraically this becomes a C infinity M module. And we know by the Serre-Swan theorem that there is an equivalence between the category of vector bundles and the category of finitely generated projective C infinity M modules. So our generalization of the notion of vector bundle will be a finitely generated projective left A module. Okay. And then, of course, we have maps, linear maps between bundles, and these correspond to C infinity M linear maps between C infinity M modules, and these will become left A linear maps. So this is the setting. Categories that will pop out during this talk will be, well, of course, we have left modules and right modules, denoted with the A in the corresponding position. And then we have these full subcategories, the category of finitely generated projective, which is the one that corresponds to the notion of vector bundles, as I said. And then we have the notion of the full subcategory of projective modules and flat modules. And mind that projective and flat are not geometric adjectives. So, for example, flatness, that has nothing to do with flatness with respect to a connection. So it's a much weaker property, this one. It sort of corresponds geometrically to a local triviality of the bundle. So it's satisfied by every bundle, of course, because bundles are far more regular already. Sorry? In the algebraic homology. So flat as a module, meaning precisely that the functor tensoring by the module is exact. Exactly. Perfect. Okay. Yeah, I want to stress that it's not a strong property as geometric flatness, because we use a lot this and it's very weak, usually. Far more is assumed. Okay. So far I have talked about the sort of topology of the object, but I haven't talked about the differential part, and here is where it comes into play. In order to give a notion of differentiation, we start from, we endow the non-commutative, not necessarily commutative algebra with an associative graded algebra, an exterior algebra. What is an exterior algebra? It's associative graded algebra, such that the 0th grade coincides with the algebra itself, and it's endowed with a differential that is a k-linear map which satisfies it squares to 0, and it satisfies this graded Leibniz property. And then we have this property of surjectivity, which means that the whole algebra is generated by the degree 0 and the image of the differential. Okay, so basically this coincides with the definition of exterior algebra in classical differential geometry. The only property that's not appearing is the graded commutativity, of course, because that would imply that A has some commutativity property that we don't want. We want to work in far more generality. Okay, examples that we have to think of for this object are the classical de Rham complex, and a more non-commutative object would be the so-called universal exterior algebra. Now, I will not use the full universal exterior algebra, so I will just give you an idea of how it works through the degree 1, basically. I'll show you how it works there. So the universal exterior algebra in degree 1 is defined as the kernel of the multiplication of the algebra. Kernel of this multiplication with differential that maps an element in A into this nice algebraic property, algebraic formula. Now, this is very nice, and in fact it's too nice because it doesn't have any geometric no geometric properties related to it. But the good news is that the word universal is not there by chance, and in fact it satisfies a universal property, meaning that if we take any exterior algebra over the same non-commutative algebra A, then we have a unique surjection that preserves the structure of exterior algebra. And in particular, we can see how the surjection works in degree 1. So it maps A tensor B into A dB. And this is unique, and we'll use this for the construction of the one jet. Okay, so now that I have introduced a bit the non-commutative context, I will start talking about the differential geometric part, so the classical theory of jet bundles. So I will not be very precise here, just to give an idea of what jets are. Given a vector bundle E over a smooth manifold M, the associated n-jet bundle is a bundle of essentially nth order approximations, by which I mean that the fiber of this bundle over a point P consists of equivalence classes of sections of the bundle up to contact of order n. Okay. They're useful because they provide, they usually are described as an intrinsic notion of, an intrinsic formulation of Taylor approximation. And once we have Once we have a notion of jet bundle, we can use it to study differential operators, and we can formulate a theory of a differential equation, and we can actually deal with it. So this is the main motivation why we're studying jets in non-commutative geometry. We would like to replicate these results for non-commutative geometry. Okay, so a jet bundle automatically comes with several maps. So the first map is the so-called prolongation, which maps a section of E into its nth order approximation, essentially. Besides this, we have the so-called jet projection, which act as a sort of forgetful operation. So we take an nth order approximation and we map it to an nth order approximation. So we lose information. Okay, so these are two maps we automatically have. And the good thing is that this is a functor. So if we have a function map of vector bundles phi, we have an associated map between the jets. And all the maps I described before are natural with respect to this functoriality. Okay.
The first one is an inclusion.
This, yes. Yes, it's between the sections.
But you consider analytic sections? Because for all smooth sections, they might have all jets original.
But we can always forget the nth order approximation by prolongation. And so it's algebraically. No, but it's even more than a section in this case. It's an algebraic section, meaning that it has a left inverse. So it's very regular. It is a monomorphism. It's very.
You consider those sections which
Okay. Yeah, yeah. Yeah, that's yeah, exactly. Okay, and so these maps I described are actually natural transformation, and these are properties that we would like to have in a generalization of jets. So composition of projection must be a projection, and prolongation composed with a projection must be a prolongation of lower level. Okay, so our aim is to find the notion of jet bundle for noncommutative geometry, and how do we plan to achieve that? We do so by using this property of the jet bundles, which is that they fit in this short exact sequence, where this is the bundle of symmetric forms. And here we can see why it's said to be an intrinsic formulation of Taylor, because we can see that the difference between the nth order approximation and the nth minus 1 is essentially homogeneous polynomials of degree n pointwise. Okay. Okay, so starting from this short exact sequence of bundle, we get this short exact sequence of C-infinity and modules. And by Serre-Swan theorem, we know that studying one is equivalent to studying the other in the category of projected and finitely generated modules. Okay, so the plan is to generalize that sequence in noncommutative geometry. So first we need to find these two functors, which is a functor that generalizes the functor of symmetric forms and the functor of jets. And then we need an inclusion of the symmetric forms into jets, prolongations, and we need them to satisfy this property. And of course, we need a notion of prolongation satisfying the same two properties I've showed before. Okay, let's start from the generalization of symmetric form, and I start with an apology because once more the word quantum is appearing in mathematics. And the reason why we put quantum is because in general the symmetry will not be the same as the same that we are used to work with, so we can't swap things around. We will have a symmetry induced by the exterior algebra, but that will not be the standard symmetry, hence the word quantum. Okay, so in classical geometry, when we want to describe a form valued in a vector bundle, we can see it as sections by tensors. So it makes sense to define these tensors as mapping a bundle into the forms valued in that bundle, interpreted in this as this module, basically. Okay, given these, the notion of functor of quantum symmetric forms is defined this way. So the degree 0 will coincide with the degree 0 of the exterior algebra, and that will be just the identity. The degree 1 also will coincide with the exterior algebra, and that will be the tensor we just defined. And for higher order, we define them by induction using this formula. So we compose these two maps, and we take the kernel, and the kernel will be the SND. Yes, so the way it works is Sn is embedded into omega 1 Sn minus 1. So we take that inclusion in the lower level, we apply the functor omega 1, and then we wedge on the first two components. This will be the map, and we take the elements that vanish applying this wedge. So this is the symmetry that the exterior algebra is providing. And we see it's a good notion because under very mild regularity assumptions, we have these equivalent formulations, and this in particular is what one would expect. So the symmetric algebra is the intersection of the kernels of the wedge applied in each position. So this is the founding idea. The reason why we chose the inductive formulation is that it allows us to, without any extra assumption, to define the Spencer complex, Spencer delta complex, and its cohomology. And we do so by this composition. So again, it's so we embed the SH into omega 1 SH minus 1. We apply omega H, and then we apply the wedge to the first component. And this is the map, which is the differential of this complex. This is the complex, which is called the Spencer delta complex, and its cohomology will be called the Spencer cohomology. Okay, so let's start building the actual jets. We start by the simplest case, so we start from the one jet and with the universal exterior algebra. And also we start for E equals A, which means in classical geometry it's the trivial bundle, of course. Okay, so we have a natural short exact sequence that we can build using this definition. So since it's been a few slides ago, I recall that omega 1 of u was the kernel of the multiplication, and I just defined the S1 to be equal to omega 1, which means the one jet short exact sequence has this form, and if we put the multiplication here, this is a short exact sequence. Okay, so we can consider this to be the one jet short exact sequence, and notice that it's the free one-dimensional A by module particular. We take as the projection the multiplication, and we take as universal prolongation the map that this map basically, which notice it's not left A-linear, it's only K-linear, but it's right A-linear. And it splits the sequence. Okay. So now we start from this jet, the universal one jet exact sequence, and we would like to now generalize it to any differential calculus, any exterior algebra. Okay, so we start by considering the universal property of the omega 1 of u and the equality map between of A, the identity of A. Okay, so if we see them as left A modules, A is a projective module, so in particular this extension is unique, and there is this couple of morphisms extends uniquely to a morphism of extensions, of left A-linear extensions. So now if we consider the kernels and the co-kernels, we define this ND as the kernel of this map, and then we have these two mysterious objects. But if we apply the snake lemma, we see that actually this object is bound to be 0 and this object is bound to be ND. So that's what we are doing. And in particular, we see that if instead of choosing any isomorphic copy of ND, we consider exactly ND, we also have that ND is is embedded in here through a composition of A bilinear maps, which means this map, if we quotient by this inclusion, we will get a bilinear a bimodule, and every map in the diagram is actually a bimodule map, although we constructed it as a left module map. Okay, so this will be our definition of one jet, and we take as a jet prolongation the composition of the universal jet prolongation with this projection to the quotient. So this is the idea. So explicitly we have that the projection is given by the multiplication in this class, and the prolongation is given by this formula. Okay, so now if we want to extend it to every module E, we just have to tensor, and since this is a split sequence, it will still be exact once we tensor. And this is the ND, yes, is the kernel of the universe, the unique epimorphism from the universal calculus to any calculus. It's can be interpreted as a sort of differential relations between forms. Okay. Okay, so it remains exact, and this will be our notion of one jet. Okay, once we have the one jet, we can do as in classical geometry, so we compose the one jet with itself n times, and we get the so-called non-holonomic n-jet functor. The n-jet functor is associated with a non-holonomic jet prolongation, which consists of the composition of the jet prolongation in each component, and practically what it looks like is we map an element E into it's basically a huge tensor power with ones at the beginning and the element at the end. So this is how it looks like, what it looks like. Okay, and the projection, we have several projection, and these will be the multiplication in each component, in each different component. So this is the notion of non-holonomic jet that we have. And now we would like to study the holonomic version, which is a different story. Okay, let's start from the two-jet. Two-jet, we wanted to satisfy this short exact sequence. And we would also like, as in the classical case, we would like it to be included or, in a sense, related to this other short exact sequence, which is the non-holonomic two-jet exact sequence, and it can be seen also as the one-jet exact sequence applied to this module. We can see that there is the omega-1, there is the one-jet applied to the one-jet, and then there is the one-jet. So we know it's exact because it's exactly what we just constructed applied to this module. Perfect. So we, as I said, we would like it to be related, and this is the relation we have. And now what we do is, assuming omega-1d flat, we get that these maps are always inclusions, so we can work in for a bit more regularity. And asking also that the two-jet prolongation is related to the non-holonomic jet prolongation, we finally get this sub-bimodule generated by the image of the prolongation, which must be there because we want to have a prolongation, and therefore the image must be inside the two-jet. And we also want the two quantum symmetric forms to be in there. So this is, in a sense, the minimum we can ask, and turns out it's exactly what we want. So this satisfies the two-jet exact sequence. So this will be our two-jet. But we would like to see it in a more implicit way. And it turns out that the two-jet can be seen as the kernel of this operator at the tilde. Operator which is defined in this space, which is as a right-hand module, it can be seen as a direct sum, but as a left-hand module, it has this non-trivial action, which has, of course, it has the standard action, but it also has mixed terms that switch things around. Okay. So explicitly, this is the form of this operator. This is the first component, and this is the second, and this will turn out later. It will be extremely important for our definition. Okay, so we can finally define the n-jet. So inspired by how we define the symmetric the functor of quantum symmetric form, we use a similar inductive definition. So we define it again as the kernel of this operator, and where Ln here is the inclusion of the nth jet into J1, Jn minus 1. Okay, so again, how it works is we take this the inclusion in the lower level, we apply J1. At this point here, we have a J2 non-holonomic, so we can apply the add operator. And this is how we get this composition, and its kernel will be the holonomic n-jet. Okay. So it's natural to consider the composition of all these inclusions until we get from Jn to the non-holonomic jet. And in general, this will not be an inclusion unless we ask some flatness condition on omega 1. And this is a situation that also happened in the setting of synthetic differential geometry, so it's not so outrageous, let's say. Okay. Furthermore, it turns out that the jet prolongation, the non-holonomic jet prolongation, factors through this kernel. So it produces a prolongation which we'll call the holonomic jet prolongation. Okay, so now we have all the required tools. A jet projection will be defined by taking Jn, embedding it into J1, Jn minus 1, using the map I just defined, and then applying the projection of the first component. So very natural, very easy, very nice. Good. And then by composing jet projection, we get the more general ones from degree n to degree n. So this is how it works. Now we can embed the Sn into the Jn by this inductive definition. I will not spend too much time on this, but it's very naturally defined, let's say. And at this point, we are finally at the most powerful result of the paper, which is essentially proving that our notion of jet satisfies the short exact sequence as we wanted. Okay, I will point out a bit the hypotheses we are using, and they're not too strong because like flatness, as I said, is a very weak condition. Usually far stronger conditions are imposed on the algebra, for example, that it's projective, finitely generated, and everything. And the other condition that sounds a bit stronger is the Spencer cohomology, but it turns out it's not actually, because classically the meaning of the vanishing of the Spencer cohomology is associated to a solution, to the integrability of a differential equation. And let's remember that these functors are applied on bundles essentially, and a bundle is nothing but the solution of the trivial equation. So of course it's integrable, of course we can find a solution. So we expect a reasonable notion of vector bundle to have vanishing Spencer cohomology anyway. So this will also provide a way of saying when an exterior algebra is a nice exterior algebra, because it will behave exactly as in the classical example. Okay, so this is the result. We don't have the full short exact sequence unless also the Spencer cohomology in degree n minus 2 will vanish, in which case everything will work perfectly. So I will show you a bit the proof. So we have defined this complex. So far it's just a complex. We have already defined these objects. And we can show that it can be inserted into this other complex. Now, I haven't defined what this object is, and we don't really use it, but broadly speaking, the way we define this object is we start from the same setting as what we used to define Jn. So we have J1, Jn minus 1, but instead of applying the full add operator and finding the kernel, we only apply the first part of it. Remember that the add operator had two components. We only apply the first component. And this turns out it corresponds to the classical notion of sesquiholonomic jet, which is not very used, but it was useful for us. What we know about it is that if we have the n-1 holonomic jet exact sequence, then we have the nth sesquiholonomic jet exact sequence, which looks exactly like this. So now if we take these two maps, so we see that by definition, Sn is the kernel of the wedge in the first two components, as I said. And Jn, since it's the kernel of eth, it's in particular also the kernel of eth in this restriction, let's say. Okay, so we don't really like this because these two objects are different. We don't relate them too well. But it turns out that since we chose this to be the space where the first component of the eth operator vanishes, and the first component was being mapped here, actually the image of this object is not in the whole space, it's just in the second part. So now these two objects are the same and we can relate them. Moreover, notice that the wedge that we had here is nothing but the minus the Spencer operator. Spencer differential, sorry. We can do better. We actually can prove that, well, of course, the image of this object lays in the kernel of the higher order Spencer differential, but it turns out also this does. So this is what we actually have. So we have the kernel of the n-2 Spencer differential in both places. And now we can take the cokernel. What does cokernel mean? Cokernel means that we take the kernel quotiented by the image, but that is precisely Spencer cohomology. Finally, now you know the trick, we apply again the snake lemma, and we get the sequence that we were looking for. And in particular, notice that when Spencer cohomology vanishes, we have the short exact sequence. Okay. Final result of this presentation is the notion of stability, which basically says that under, again, very weak assumptions, or very reasonable assumptions, as in this case, we have that the non-holonomic and the holonomic jet functors preserve the subcategories of flat modules, projective modules, and finitely generated projective. And why is this theorem important? It's important because it tells us that if we start from a vector bundle, that is a finitely generated projective bundle, applying the jet functor, we get again a bundle. So we have a jet bundle, basically. Okay. Thank you very much for your attention, and stay tuned for the second part of this talk. Yes. The universal so in the universal calculus, what happens is that the functor of quantum symmetric form becomes trivial in degree higher than 1, because the exterior algebra coincides with the tensor algebra, essentially. And so everything becomes trivial up to order 1, and in order 1, I think it does work. Yeah, it works. Yeah. So yes, it's a reasonable notion also for noncommutative geometry, I think. Yes. Sorry, and? I don't know. But, yeah. Okay, I don't know the details, but I can think of it. Yes. Yeah, Henrik, will you show the Spencer cohomology in your talk? I don't know, but we have yeah, okay. Maybe we have an example, you see, next talk. No, but yes, it's a reasonable assumption. Like every algebra we tested it on that has some meaning has vanishing Spencer cohomology. That's why it was a nice finding, because it's something that doesn't appear normally in non-commutative geometry, and looks like a property that one would want from an exterior algebra. Yes.
One last question. Is there anything we need to remember from this talk
Okay, I'd say everything, but okay, let's see. Harry, do you have some special requests for? Perfect. So we'll already. Perfect.